Chapter 13, Lesson 1. In this chapter, we'll talk about solutions and their properties. So, a quick definition of what a solution is. A solution is a homogeneous mixture of two or more substances. Recall that homogeneous means it is perfectly mixed with equal proportions of substances throughout the whole solution. Now, any solution has two parts. The solute is what is dispersed in the solvent. So the solvent is what's doing the dissolving, and the solute is what is dissolving. And most of the time, you have more solvent than you have solute. And the way to think about this and remember it, you can think about the word solute having 1, 2, 3, 4, 5, 6 letters, and the solvent having 1, 2, 3, 4, 5, 6, 7 letters. So what you have more of is what's doing the dissolving. Now, solutions don't have to be simply a liquid and a solid. In fact, what you see is you can have two gases, two gases. Both the solvent and the solute could be gases. And an example of this is the air around us. You could have two liquids mixed together. This is alcohol and water, for example. The most common version of a solution that we're all used to is a solid in a liquid. This is what we're used to. So this is your salt and water. But we can even have a solid dispersed in a solid. So these are alloys. Actually, silver and gold, these are called alloys. So really you can have any state dissolved in any other state, as long as it is uniform or homogeneous. Now, anytime there's a solution that forms, the solvent particles, in this case water, that wants to dissolve the salt, have to overcome the strength of the forces between these ions. And water is especially good at doing this. So the forces must be strong enough to overcome the forces between each individual particle, essentially. And when this does occur, then what we call solvation happens. And solvation essentially is whenever your solvent particles will surround your solute particles and then essentially disperse them throughout the solution. So here you see that the solute particles are dispersed throughout. That's kind of the idea. And this is called solvation. Now, the reason why water is such a good substance, such a good solvent, water is very oftentimes called the universal solvent. And the reason we call it that is because it's able to dissolve a large number of substances, especially ionic salts, metal, nonmetal salts. And that's because water has very strong intermolecular forces, because recall it has hydrogen bonding operating in it. And this allows it to act almost as an ionic substance. It has a very positive side on the hydrogen and a very negative side on the oxygen, and this allows it to bond with very negative ions and very positive ions, as is the case here. So water can oftentimes overcome the lattice energy of the salt crystal. Anytime there's a solution that happens, we can break apart the whole process into individual steps. So we'll have to first separate the solute particles, the salt. We have to separate the solvent particles, the water, and then we have to form new interactions between the two. Now, anytime we do this, we can study the energetics of what is happening. Anytime you're breaking apart particles, in the case of breaking apart the solute and the solvent, this always requires energy. So delta H is greater than 0, or delta H is positive, because essentially we're breaking bonds. So anytime you're breaking bonds, energy is put into the system. So in both steps 1 and step 2, we're putting energy into the system as we're breaking the intermolecular bonds between the substances. And then 3, when we form new interactions, when we dissolve essentially, then anytime you form a bond, heat is released. This is an exothermic process. So delta H is less than 0 or negative. So the formation of a solvent and solute together is an exothermic process. Formation of a solution, that is. So then the overall change in the solution can be thought of as adding these 3 heat changes, breaking apart the solute, the solvent, and then making new solute-solvent interactions. So for example, anytime you dissolve sodium hydroxide, this is a very exothermic process, just by dissolving solid sodium hydroxide in water, releases 44.48 kilojoules per mole. Your beaker, as you're doing this, gets substantially warm, and you have to be real careful, actually, that you don't damage yourself. And when ammonium nitrate is dissolved, the opposite happens. Now, this is actually an endothermic process, so the solution gets quite cold, very noticeably cold. 26.4 kilojoules is required to make this whole thing happen. So it can either be exo or endothermic, depending on the individual steps involved. Now, here's a good point to consider. Anytime you're dissolving is actually a physical change, or dissolution is a physical change. So sometimes, if you, for example, take a metal, in this case I think this should be nickel metal. If you put nickel metal in hydrochloric acid, what will happen is the nickel metal eventually will dissolve. The solution will turn green, and then it looks like the nickel dissolved, but actually it reacted, because then when you get back the substance, it's no longer metallic nickel, it is nickel 2+, it is this salt. So watch out, not every dissolution is a real physical change. It could be a chemical change like this. Okay, let's talk about three types of solutions. We have a saturated solution. Essentially what this means is that the solvent holds as much solute as possible, so no more can dissolve, is the idea. And in a saturated solution, what you have is a bunch of undissolved particles at the bottom of the beaker. Oftentimes you can see like a powder that cannot get dissolved. That's because the solution holds a maximum amount of solute, and this is called dynamic equilibrium. It turns out actually more is dissolving, but at the same time more is coming out of solution, so that's what we mean by equilibrium. In an unsaturated solution, the solution can hold more solute if you add more solute. So it has less solute than it can hold at a particular temperature. And we'll see how temperature actually affects the amount of solute that can be dissolved. So temperature is actually an important factor here. In a supersaturated solution, finally, this is the most exciting type of solution. The solvent holds more solute than is normally possible. In other words, this solution has much more salt dissolved in it than it can hold. And the way this was achieved is we increased the temperature and dissolved much more in the solution, and then we decreased the temperature, and the solution held all those dissolved particles. Very often, in the solution itself, you can feel it's very heavy. It's as though there's a bunch of solid in the solution. Very often, more than half of it is actually your solute. And this happens especially with certain substances. A famous one this happens with is something called sodium acetate. Sodium acetate is very affected by temperature, so you're able to do this. What we have here is they're actually dropping a little tiny crystal into the beaker, and then you have the process of crystallization happening. You get that solid coming out of the solution before your eyes, and this takes a matter of seconds, and then you'll get all that solute back out. Now, let's talk about how and why things dissolve, and we have a saying in chemistry, like dissolves like. What this means is if you are a polar substance, if you're a polar solvent, you tend to dissolve polar solute particles. If you are nonpolar, you tend to dissolve nonpolar substances. So if you take a look, for example, here, methanol is this guy. Methanol is very polar, and being very polar, its solubility in water is infinite. It's extremely soluble in water. Now, on the contrary, hexanol here is pretty nonpolar. You could say not very polar. So its solubility in water is quite low. And its solubility in hexane, which is completely nonpolar, is therefore infinite. And what you see here essentially, the more polar the molecule, the more it dissolves in water. The less polar it is, the more it dissolves in this nonpolar hexane. This guy here is hexane, famously contrasted with that of water because it's so nonpolar. And so the more similar the interactions, the more likely the substance it dissolves. What you have here is a picture of hydrogen bonding. So you have a substance here that has an oxygen and a hydrogen, therefore it can form hydrogen bonds with one another. So if two substances have hydrogen bonding ability, they will dissolve in one another, is the idea. Here's a contrast of something called cyclohexane, which is nonpolar. This is perfectly distributed to be a nonpolar molecule. And then you have glucose, which is a sugar molecule, which has many OH groups. Notice 1, 2, 3, 4, 5 OH groups, which makes that molecule very soluble in water because it can participate in hydrogen bonding with water. Sugar, as you know, is very soluble. So we can even take a look at more complex molecules. These are biomolecules. So vitamin A and vitamin C compared. Vitamin A has a very big nonpolar region here. This is nonpolar. Whereas it has a small polar region. And vitamin C, on the contrast, has a very big polar region. Most of the molecule is actually polar. Therefore, it is very soluble in water, and vitamin A is slightly soluble. We can't say that it is insoluble because it does have this polar side to it. So this is actually very important whenever you're preparing a substance to make sure it is soluble in water so it can go into your body, since your body is mostly made of water. Now we can also talk about gases being dissolved in solution. And here it says, in general, the solubility of gases increases with increasing mass. That's because the bigger the gas, the stronger its London dispersion forces, and the more it can bond, essentially. So large molecules will actually dissolve better than smaller molecules. And you probably know that gases do dissolve in water. Really, any solution of water, even if it's sitting on your tabletop, has a bunch of oxygen dissolved in it already. In fact, that's how a fish can survive in water, is because of dissolved oxygen. So we can do an example problem. Predict whether each of the following substances is most likely to dissolve in carbon tetrachloride, carbon tet as we call it in the business, or in water. Now, carbon tetrachloride is actually a nonpolar molecule. So if you take a look here, carbon tetrachloride looks like this, with 8 electrons around every chlorine, so it is nonpolar. Water, famously, is polar. So what we've got here, why don't we begin with C7H16. Now this is something called heptane, and this has 7 carbons, essentially aligned in a row with a bunch of hydrogens around it. And if you count the number of lines here, you'll find it is 16 lines. So because this is also nonpolar, it will dissolve very well in carbon tetrachloride. So this guy will be then very soluble in carbon tetrachloride. The other substance here that's soluble in carbon tetrachloride is iodine. Iodine, diatomic iodine, is simply 2 iodine atoms bonded together, and it is also nonpolar, and for that reason it will also dissolve in carbon tet. Iodine is actually a solid, but it'll dissolve quite readily in this nonpolar carbon tetrachloride. On the other hand, we have here HCl. HCl is an acid, and it's famously polar because you got your H and your Cl. The difference here is quite large, so this is definitely a polar molecule. So this will dissolve very well in your water. In fact, you can create a very high concentrations of hydrochloric acid in water. Hydrochloric acid comes in a 12 molar stock solution, which means you get 12 moles in a liter of water. That's quite a bit dissolved in there. And then finally, sodium sulfate. Because this guy is ionic, ionic substances will dissolve in water, as long as, if you recall, the solubility rules allow it to get dissolved. So this one is also soluble in water. A bit messy here, but I think we can see the correlation. Essentially, like dissolves like. And finally, let's finish this lesson with talking about some factors affecting solubility, and we've glanced at these already. So, first of all, let's take a look at temperature effects. We know that hot water will dissolve more sugar than cold water. So, in general, as temp increases, the solubility of solids in general increases. Rarely there's an exception to this. Rarely you can have a substance. Here's cerium sulfate. Cerium is actually from the F block. Very strange metal, very strange rare earth metal. But for the most part, it's a direct relationship. And actually here is a graph showing many different substances and the solubility of those substances in terms of temperature, as temperature increases. So you'll see that most of these substances, their solubility actually goes up with an increase in temperature. Now famously, salt, this is regular table salt, sodium chloride, is the least affected. Famously, salt, if you increase the temperature from, say, 0 to 100, its solubility just goes up a little bit. But there are some substances where it's actually an exponential increase, quite a bit of an effect there. For gases, temperature has the opposite effect. If you increase the temperature, the solubility of a gas goes down, as you can see the trend in these graphs, really for any one of these gases. And so this is why if you want to keep your beverage nice and carbonated, if you want CO2 to remain in your MD, Mountain Dew, you put it into the fridge, if it's been open, we'll say it's open, into fridge, and the decrease in temperature will actually increase the solubility of the gas. And this actually has environmental effects. So if lakes, for example, get too warm, then both oxygen and carbon dioxide become less soluble, and little fishies actually have a hard time breathing, and they don't do very well, because the oxygen leaves essentially the lake. And CO2, plant life and algae and the like does not like it getting warm either, because CO2 leaves, and plants and animals aren't able to survive. Let's take a look at pressure effects. Really, pressure only affects the solubility of gases. It has really no effect on the solubility of liquids and solids, but it has a pretty big effect on the solubility of gases. And then technically, it is directly proportional. So the higher the pressure above the liquid, the more gas is dissolved. And this is really just logical. The more gas you have above, if you increase the pressure here, as in the bottom cylinder, you just have more gas above the liquid, so more of it gets dissolved. In fact, soda cans are bottled, or soda bottles, under high pressure. And whenever you open up a soda can, what you're doing, or a soda bottle, is you're decreasing the pressure, and that's why a lot of that initial gas comes out. So, because these are bottled under a few atmospheres of pressure. And this could be modeled by Henry's law, which simply is a mathematical equation showing you that the solubility of your gas increases with pressure, is directly related to pressure. In fact, if you rearrange them to solve for the constant, you'll see that the solubility divided by the pressure gives you a constant. And remember, this is a direct relationship where the solubility goes up as the pressure goes up. And you can find constants for different gases, and you can see that this is a direct relationship. We're not going to do too much with this equation, but just to say that this is a direct relationship. And I believe that completes Lesson 1 of Chapter 13.